Well, thank you very much. It's really a pleasure to have the chance to kick off tonight's festivities, and I'd just like to start by thanking Dr. Saran and also Narit for putting together this fantastic event, one in which I'll get to talk about something that is truly my favorite subject. I'm not going to try to convince you that we know for sure that life exists beyond the Earth, but what I am going to try to convince you of is that we're on the cusp of making that discovery. And whatever the chances were of making that discovery 10 years ago, the chances today are thousands of times greater. The image that you see here is one of the most famous in astrophysics. It's called the Hubble Ultra Deep Field. It was taken by using one of the most powerful telescopes that human beings have ever produced, the Hubble Space Telescope, and pointing it at a little tiny patch of sky, an otherwise unremarkable dark patch of sky, about the size of the head of a pin held up at arm's length, and collecting light from that patch of the sky for hundreds and hundreds of hours. And all of the points that you see here in this image are not stars, but in fact are galaxies, each with hundreds of billions of stars in it. And by taking this image and extrapolating to the rest of the sky that the telescope didn't observe, we've learned that just in the part of the universe that we can see, there are literally hundreds of billions of galaxies, again, each with hundreds of billions of stars. And we've learned some remarkable things about the universe just in the last few decades. First and foremost, we've learned that planetary systems are incredibly common. 25 years ago or 30 years ago, we had no idea whether planets were the rule or the exception. But we now know that every star in our galaxy has a planetary system, and we have no reason to believe that other stars and other galaxies are any different. And even more important than the fact that planets are as common as they are, we know that something like 1 in 5 stars hosts a planet about the size and the temperature of the Earth. That is a planet that could have liquid water on its surface and could host life as we know it. We've also learned something very, very exciting just in the last couple of years, and that is that there's a tremendous amount of material exchanged through planetary systems, between planetary systems. And just about a year and a half ago or so, we discovered the first interstellar object, the first object that we ever found in our own solar system that didn't form with all of the planets and asteroids that we know about. In fact, this object, Oumuamua, came to our solar system from another star, and we now believe that there are thousands of these objects interacting with our solar system even as we speak. But with respect to the biggest question that I think all of us ask when we look through these telescopes here, or we just stare up at the night sky, is there other life in the universe, a dark forest? We don't know what's out there lurking in the trees for us to find. But we have many reasons to be optimistic about the possibilities for life. Very interestingly, we know that life began very, very quickly on the Earth. Essentially, as soon as the Earth was cool enough for the biochemical processes that drive life today to exist, life was thriving on the Earth. And we know that from fossilized colonies of bacteria, like the ones that you see here called stromatolites. The Earth is about 4.5 billion years old, and within a few 100 million years, for all the life that we have on the surface of the Earth. But here, this life actually gets energy from chemical reactions surrounding this hydrothermal vent and drives a whole ecosystem of life completely independent of the sun, something we truly did not expect even several decades ago. And we see these environments in our own solar system. This is a moon of Saturn called Enceladus. And from images of Enceladus and other measurements, we know that Enceladus has an icy surface and probably liquid water beneath that icy surface. So while the presence of habitable planets that are about the size of the Earth and the right distance from from their star to have liquid water on their surface is surely very, very important. Even that might not be necessary for life to begin and to thrive in environments far, far removed from the surface of a star. And we also know that life went on to develop incredible complexity, certainly as evidenced by all of us gathered here. Our own life here on Earth has developed not only complexity, but also technology. Technology that could be detected at interstellar distances, to the distances of other stars, if other civilizations were looking back at us. So if you asked most astronomers how we could go about trying to detect life on other worlds, they would probably talk to you about one of two options. Of course, as many of you probably know, we can send craft to other bodies in our own solar system, robotic spacecraft that can land on the surface of Mars, for example, can dig into the surface of Mars and search for some evidence of biology. This is a very powerful method. You can basically pack a chemistry set or a petri dish on that spacecraft, and you can sample to see if there's any biology going on in that environment. Another very exciting method of looking for life is called looking for spectroscopic biosignatures. And basically that involves taking something called a spectrum of an exoplanet atmosphere of a planet orbiting another star and examining the chemistry of that atmosphere and seeing if there's any evidence of what we call disequilibrium, some kind of environment that's out of equilibrium with the natural surroundings and driven by biology. Of course, this is something that we see in our own atmosphere because of all of the life that we have here on Earth. But there's another way of looking for life, and it's the method that we're going to be talking about today, and that's to look for something called technosignatures, evidence of technology. For the last 100 years or so, human beings have produced technology that could be detected at interstellar distances if other civilizations were using telescopes like the ones here on the roof to look back at the Earth. So in the search for extraterrestrial intelligence, we turn that idea around and we imagine that if other civilizations have developed technology similar to what we have here on Earth, perhaps omnidirectional radio transmitters or powerful lasers, we might be able to detect that technology with our telescopes and thereby infer the existence of extraterrestrial life, and in particular, intelligent life. So there's a very interesting calculation that you can do with regard to these three methods, which is very illustrative of the power of the three methods and how complementary they are. So sending robotic spacecraft to other bodies in our solar system is surely a very, very powerful method, but of course we're limited by how far we can send those spacecraft, and for the moment we can't send them anywhere beyond our own solar system. The other method I talked with you about, looking at spectroscopic biosignatures at exoplanet atmospheres, we know those exoplanets are out there, we can look at their atmospheres. That sounds really, really good, but it turns out that that's an incredibly difficult measurement to make. And even with the next generation of space telescopes that will be coming online in 2030 and 2040, like a telescope called LUVOIR, there are only a few dozen stars and exoplanets that would actually be amenable to measuring in this way. But if you compare that with technosignatures, you discover something really incredible. So if you take one of our large ground-based telescopes, like the Green Bank Radio Telescope in the United States, and you imagine looking for something that is equivalent to the most powerful radio transmitter that we have here on Earth, like the Arecibo Planetary Radar, you discover that you could actually detect that signal out to 10,000 light years. That's 10 million times more stars than can be probed with either of the other two methods. So while very simple life, bacteriological life, might be far more common in the universe than intelligent life, the volume that we can probe in our searches for intelligent life is much, much larger. And that means that all of these methods are very much in a race, and it's not at all obvious which one will succeed first. So we've arrived at a really incredible time in the history of human civilization. Not only do we know without a doubt that everything necessary for life to exist is common throughout the universe. There are lots of planets, lots of organic molecules, all of the things that we think are necessary for life to emerge and to thrive and to evolve. But we also have the capacity to search for life in truly incredible ways, including searches for intelligent life. And this is something that was realized in a really profound way in the summer of 2015 with the announcement of something called the Breakthrough Initiatives, a series of scientific investigations focused on trying to answer the question, are we alone? Is there other life out there in the universe? The Breakthrough Initiatives are sponsored by the Breakthrough Prize Foundation and principally by a wealthy investor from Silicon Valley named Yuri Milner there on the left. And when the initiatives were announced, Yuri was joined by the late Stephen Hawking, Martin Rees, the astronomer royal of the United Kingdom, Frank Drake, and also the widow of Carl Sagan, Anne Druyan. Today there are 5 breakthrough initiatives. Breakthrough Starshot, an effort to try to develop a spacecraft that could be sent at a small fraction of the speed of light to the nearest star to the Earth, Alpha Centauri, about 4.5 light years away. An initiative called Breakthrough Message, to design a message that we might ultimately send to intelligent life, should we ever detect it. Breakthrough Watch, an effort to image extrasolar planets, to take pictures of extrasolar planets. An annual conference series called Breakthrough Discuss. And finally, Breakthrough Listen, the most comprehensive, sensitive, and intensive search for intelligent life in the history of the field. And relative to the other initiatives and relative to the other efforts involved in this field, Breakthrough Listen asks a very specific question. Is intelligence a common outcome? Is intelligence a common outcome enough that we might be able to detect intelligent life beyond the Earth? The Breakthrough Listen program is funded by a 10-year, $100 million commitment. We'll study 1 million nearby stars, conduct a complete survey of the Milky Way galactic plane, and also look at nearby galaxies for very, very bright transmitters. 1 day of the Listen program is equal to 1 year of any previous search that's ever been done. And very importantly, all of the data that we collect in this program is open to the public. All of our instrument designs, all of our observing plans are all publicly available, and we very much invite the public to participate in the effort. And you can learn more about the Breakthrough Listen program and the other initiatives at the URL here shown on the slide. We've assembled a fantastic array of instruments in order to conduct this search across the electromagnetic spectrum, looking for optical lasers as well as radio signals, including some of the largest radio telescopes in the world, the Green Bank Telescope in West Virginia in the United States, the Parkes Telescope in Australia, a brand new telescope called Meerkat in South Africa, and a number of other facilities. And hopefully soon, facilities right here in Thailand will also be participating in the Listen program, searching for extraterrestrial intelligence. In addition to very powerful telescopes, very powerful astronomical facilities, we're also bringing a Silicon Valley approach to this problem. We're looking at innovative ways that we can analyze data, ways that we can look for signals that we don't expect, anomalies, and ways that we can use the same kind of hardware technologies and software technologies that are driving internet commerce to search for intelligent life in even more profound ways. Now, I'd like to end with a little bit of math here before I hand the microphone over to my colleague, Professor Garrett, and that is to talk with you a little bit about the Drake equation. So Frank Drake, here in the top left, in about 1960, devised something called the Drake equation, an equation that tries to quantify the various factors that would go in to the emergence of a communicative, intelligent civilization that we might be able to detect. N, here on the left, the number of civilizations that we might be able to detect, is expressed as the product of a number of factors. So our star there is the average rate of star formation in our galaxy. Of course, you probably need stars to have life. FP, the fraction of stars with planets. FE, or any, the number of Earth-like planets per system, and it continues with a number of other factors. And I just wanted to point out one factor in this equation that you might not guess would be there. At least, certainly I didn't guess that it would be there when I first looked at this equation, and that's L, the length of time that a civilization exists. It could be that the most important factor in whether or not we ever are successful in detecting intelligent life beyond the Earth is not the number of stars with planets or the number of Earth-like planets in the galaxy, but how long can a civilization last? How long does that civilization remain detectable? And with that, I'll hand it over to Professor Garrett.
Okay, it's a great pleasure to be here today. I've been here for a couple of days looking at some of the telescope facilities that you have here. There's a large radio telescope being built just about 40 minutes away from where we are just now. It's amazing, you know. You're so very, very lucky to be here, living in Chiang Mai, so close to these telescopes, so close to all the young people who are going to use those telescopes and make fantastic discoveries. So it's absolutely an honor to be here today. What I'm going to talk about is actually what SETI tells us beyond just the question of are we alone. SETI also tells us things about ourselves. It suggests perhaps that we have options that we must make in the future, how we evolve as a species. As Andrew said before, the longevity of a species is very important in terms of how easy it will be to detect other civilizations. And so SETI tells us a lot more than just the question, are we alone? It tells us also about ourselves and maybe where we're going in the future. I think SETI is actually quite a difficult thing to do for a number of reasons. It's certainly trying to detect signals from civilizations that are similar to our own. That's probably something that's quite difficult. And I want to share some of the reasons why I think what Andrew is doing is a really tough thing to do. First of all, just our own galaxy, so the Milky Way galaxy here, is really, really big. It's so big that we cannot really comprehend just how big it is. You know, the distances between stars are absolutely enormous. If we were to be able to travel at the speed of light, which we believe to be the fastest speed that anything can travel at, then it would still take us 60,000 years to go from one side of the Milky Way all the way across to the other. So although it's filled with, you know, at least 100 billion stars, the distances between those stars are truly enormous. So if we have civilizations in the Milky Way, they may be separated by really, really large distances. So that's one problem. And the other problem that isn't always fully understood is that although we think the speed of light is really, really fast, especially locally here, for example, in this room, it takes a tiny fraction of a second for light to travel across the room from the lights over there. When you begin to operate on astronomical scales, even short astronomical scales, like the distance between the Earth and our nearest neighbor, the Moon, then you begin to see that the speed of light is not quite as fast as we all feel that it is. So it takes a few seconds, for example, for a light beam or a radio wave to go between the Earth and the Moon and back again. And if you go to the nearest planet to the Earth, for example, Mars, then you might not be able to see it, but here's a radio wave or a light wave. It takes typically about 20 minutes to go from the Earth to Mars and back again. And these are objects that are really sort of in our backyard. They're in our astronomical garden. When we start thinking about the nearest stars, the travel times become years, then many decades, and 60,000 years to cross the Milky Way. So the speed of light is quite slow. And the other problem that we have is that the galaxy is really, really old. So the galaxy is so old, it's almost the same age as the universe. It's been producing stars for a long, long time, producing planets for a long, long time. But it's quite possible that even if there are many, many civilizations that have arisen in our own galaxy, that they haven't all arisen at the same time. Especially if the longevity of a civilization is very, very short. For example, here, if we're only around for maybe 100 years, or even 1,000 years, or 10,000 years, then the chances that these civilizations will overlap in time is really, really small. And even if they do overlap, they'll be separated by really large distances. And because the speed of light takes so long to go from one part of the galaxy to another, it actually becomes really quite a tough problem to be able to detect these signals. And certainly trying to communicate between civilizations becomes a really, really tough problem. So this value of L, basically the longevity of a civilization, becomes really important, because if civilizations like our own, a technical civilization, exists for maybe 10,000 or 100,000 or 1,000,000 years, which I'm sure is what we would all like, then this problem actually becomes much easier. If civilizations are around for a long time, then there's a good chance that those civilizations will overlap and that we can pick up the technical signatures of those civilizations with the instruments that we have today. And this makes us think, the really nice thing about SETI is that it actually makes us think not just about what might be out there, but it also makes us think about what we have here on this planet and how we will evolve in the future. And we know that we have lots of challenges at the moment. These are just some of the challenges that we have. We know that we have a rising population. Very soon, the population of the planet will be of order 11 billion people in 2035, for example. We know that the climate is changing because we're putting a lot of carbon dioxide into the atmosphere. We always have the threat of war, for example, and a nuclear exchange, which would also threaten the longevity of our civilization. We have at the moment, this very interesting period where our machines are becoming actually intelligent. Could they actually overtake human beings? Could we actually become extinct because artificial intelligence sort of takes over our role and doesn't need us any longer? And then there are all the natural disasters. So for example, impacts from comets or asteroids. At the moment, we have no way to defend ourselves or our planet against these kind of natural disasters. So there are many possibilities why the longevity of a civilization might actually be quite short. And at the moment, we seem to be on this cusp. One possibility is that we continue to do the things that we're doing at the moment, that we continue to use fuels that produce carbon dioxide, that we continue to wage war with each other, that we continue to use the resources of the planet in a completely unsustainable way. We can make that choice. But that choice will lead to extinction. And unlike the dinosaurs, we will be responsible for our own extinction, at least in terms of being a technical civilization. That will stop. And we won't be communicating with anyone, not only not on this planet, but not on other planets. So we have a choice to make, because the other option is that we do become sustainable, that we actually change the way we use resources on the planet, that we continue to develop technologies and we continue to develop the fundamental sciences that might allow us, for example, to leave this planet, to use the resources better on this planet, but also to use the other resources that we have in the solar system, including the energy that we get from the sun. So the sun is just about the most efficient energy source you can imagine. And we have the possibility in the future of being able to harness that energy, an energy that is sustainable and that won't cause all the problems that we have using fossil fuels at the moment. So we have options, and it's up to you, especially the young people in this audience, to make the choice what you want to do. You know, it's really up to you. Do you want to continue the way we're going just now, or should we perhaps be doing something rather sustainably? There are a few other reasons why the SETI problem might actually be quite difficult. I think the best case is that we're just waiting for some kind of technological breakthrough. So the work that Andrew is doing is a really good example. You know, the fact that in one day, using the instruments that Breakthrough Listen has produced, the fact that we can do in one day, which previously just a few years ago took 1 year, gives you an idea of how our instrumentation is advancing. And this might be the breakthrough. This might be the capacity that's required in order to be able to make the detection. And I often think of Anthony van Leeuwenhoek. He was a Dutch glass maker, lens maker 250 years ago. He produced and built the first really good microscopes. So the microscope was an invention around the same time as the telescope, and it opened up the microscopic world. For the first time, we could actually see life that we'd never been able to see before. We'd never been able to see with the human eye. And actually, the dominant life on this planet is microscopic life, but we knew absolutely nothing about microscopic life only 200 years ago. We had to have a scientific breakthrough of the microscope before we understood, before we saw the big picture of life on this planet. So maybe we're just waiting for a technical breakthrough. The other possibility that we have to admit is that maybe we're just not smart enough, you know? Maybe we're just not clever enough. Maybe life has manifested itself in a way that we recognize on this planet, but maybe it's rather different on other planets or in space or wherever. Maybe we just don't have the capacity to recognize other intelligences that are out there. But maybe our machines will actually do a much better job. And maybe our machines will actually discover their machines. So let's hope not. Let's hope it's us detecting them, but you never know. And the other thing that I like to think about SETI is, as I mentioned before, the thing that worries me is that we haven't detected advanced civilizations yet. So when I talk about an advanced civilization, I mean one that's much more advanced than we are. It probably uses energy at a much higher rate than we do. It may travel between the stars, for example, and you need a lot of energy to be able to do that. And our astronomical instruments should be picking up those kind of advanced civilizations. So if you could imagine what else might be out there, then I think as a physicist and an astronomer, I would argue that it has to be based on the cosmic foundations that we have. So that's normal matter, all the matter that you see around you that's been produced in stars, for example, and which makes up life on this planet and this planet itself. But in addition to that, there are actually two larger components of the energy content of the universe that we absolutely don't understand. So we have to be careful in science to admit that there are many things that we don't understand, and when they combine together, we might not actually understand how they can completely manifest themselves. So one component is dark matter. We've known about dark matter for about 100 years. We've been trying to work out what it is. We still don't know. Maybe a breakthrough is coming, but at the moment we still don't know actually what dark matter is composed of. And even less is this largest component of the energy content of the universe, which is dark energy, which is accelerating the expansion of the universe. We have absolutely hardly any clue what that is. So we have these cosmic foundations. We don't know quite everything about them, but at least we know that on this planet that this happened, that we had simple life, it became complex life, it became intelligent life that tried to understand the universe and became conscious. We may be going through to branch off in another direction, which is artificial intelligence and our machines. So this is one thing that happened. But is it possible that other things have happened? That these cosmic foundations actually allow us to have a much sort of larger variety of conscious, intelligent beings or entities. So it sounds a bit like Star Trek, but we have to be kind of open to all of these things, because so far we haven't discovered a SETI signal. And we should have, especially we should have from advanced civilizations. So maybe there's something more out there and we just don't recognize it yet. So I'd like to think that, wouldn't it be wonderful if life, I mean life is a wonderful thing, but wouldn't it be wonderful if there are other manifestations of all those cosmic foundations that produce something else, something that's also intelligent, something that's conscious, but might be quite different from us, even if it's a different type of life or a different type of intelligent species. So SETI really challenges us to think, I think, in a really broad way, looking at the big picture. If we are alone in the universe, if we're the only intelligent species, which I agree with Andrew, I just can't believe that that would be the case, but if we are the only intelligent species, if we really are something special, then I think that's also telling us that we need to think about the way we live and the way we want to move forward in the future. And looking at the future, I think it's one of the most worrying aspects would be if this is all there is. If there's only life on this planet, only intelligent life on this planet, that would be really, really sort of scary. And it reminds me of a quote by Sir Arthur C. Clarke. Either we are alone in the universe or we are not. Both are equally terrifying. And I absolutely feel that. If we were alone in the universe, wouldn't that be so sad, so terrifyingly sad? But if we are not, then that's also terrifying. What do they look like? What do they think? What kind of gods do they have? Do they love each other? Do they fight each other? What kind of music do they have? What kind of literature do they have? I mean, in some way it's so exciting, but also terrifying. Do they come here and actually, eat us up, for example? There's many possibilities, but at some level, both of these options are terrifying. But I think if we are special, if we are the only intelligent species in the Milky Way, or even in the universe, which is even less likely, but if we are, then we really ought to realize that what we have here is absolutely precious. This species, all the human beings in this room, that this is a precious commodity. This might be the only manifestation of something that the universe tries to understand itself by. And that would make us incredibly special. And if we are special, if we really are the only intelligent beings out there, then we really need to take better care of this planet. And we also need to take much better care of each other. And I think what's important is that that's not just our friends and our colleagues and our families. We have to actually think that we're privileged to be on this fantastic cosmic spaceship. It takes us around the sun once a year. It takes us around the galaxy every 250 million years. It looks after us. It gives us all the privileges and benefits and the environment in which we can prosper. But we have to look after it, and we have to look after each other, and not just the people that are sitting next to us, but everyone on this planet. Thank you.